Okay, looking at some problems here involving definite integrals. This is number 7 in the book. Number 7 actually asks us to evaluate a definite integral, not using calculus, but using geometry, some formulas from geometry, which we can do sometimes. So what they ask us to do first, though, I've already done here on the paper. They say sketch the region whose area is represented by the definite integral. Okay, well, that just goes back to what definite integrals represent. If I put an integral sign here with numbers above and below, it's a definite integral. The function that's inside, we're automatically talking about the area below that curve. So since I'm integrating x plus 1, I'm talking about the curve y equals x plus 1. Okay, so that's the line here. Now, where area comes in is through the integral. If we integrate that in a definite integral from 0 to 5, that means we'd like to find the area below this curve, starting when x is 0 right here, and stopping when x is 5 right here. Okay, so what you see here, I've shaded. Okay, that's the shaded region whose area we're going to find. Okay, now to kind of keep an eye on our answer, keep in mind that every unit on my grid paper here is, or every box in my grid paper is 1 unit. So this little region here, that's 1 square unit. So you can see this area is going to be pretty big, maybe 10 or 20 square units. Okay, but what is the exact area? Okay, well, there are 2 ways you can compute an area. You can compute it using geometry, which is what we're going to do here, or you can compute it using calculus. Okay, but if you can use geometry, sometimes that's nice to do. So how would you find the area here? Okay, well, again, if you're going to use a formula from geometry, you have to get pretty lucky, I suppose, because the region has to be nice. We can talk about very strange regions that we don't have formulas for area of in geometry, and that's where we have to use calculus. But if you look at what we're graphing here, if you're careful, you might notice that this is really 2 shapes. It's a little rectangle sitting on top of a triangle. Okay, so there's my rectangle and my triangle. See, it kind of looks like a triangle if we were to cut it off right here, right? That would be just a little triangle, okay? But below that I have this little rectangle piece, okay? Well, in geometry we have a formula for area of a triangle and area of a rectangle. So I'm going to break this region into those 2 pieces and use my formulas from geometry. Okay, so what's the formula for the area of a triangle? Okay, oops here, okay. So there's a formula. The area of a triangle is base times height over 2. Okay, the base is the length of the bottom side of the triangle, and h here is the height, which this triangle, its height, that's just the distance from that base to the very highest point on the triangle. That's also the same as my side on the right here in this problem. Okay, so base times height over 2. That's from geometry. Okay. Well, what is the base and height of this triangle? Now you have to be careful here because the triangle only goes down to this portion. So the base is the distance from right here on the y-axis all the way to the right. And of course you can count that. That's 5 units. Okay. So I'll take 5 times the height over 2. Okay. But again, this is the base of my triangle, so to get the height I need to count up to the top point on the triangle. And that's 1, 2, 3, 4, 5 units again. Okay. So the area of this triangle is 5 times 5 over 2. That's 25 over 2 square units. Okay. And again, if each box was 1 foot by 1 foot, it would be square feet, but we just call it square units here. Okay. Okay, and that's what? That's about 12.5 square units. Okay. Well, we also have this little rectangle in here, and this rectangle, if you look, it's 1 unit tall. Okay, so this length here is 1. Okay, and the width of the rectangle is 5 units. Okay, and you might remember the formula for the area of a rectangle. People tend to remember this one. They use it a little bit more often, but it's length times width. Okay, so we've got 1 times 5, which is 5. So that's 5 square, let's say square units. Okay, so what's the area we wanted to compute? And by the way, remember, this is just the area of the square, this is the area of the triangle. What's this whole area that we want to find, given by the definite integral? Okay. Well, see, we didn't actually use any calculus here, we just used geometry, because really this is asking us to compute an area. Okay. Well, it's going to be the area of the triangle plus the area of the rectangle. So that's 25 over 2 plus 5. Okay. So we like to use exact answers when we can. That's 25 over 2 plus 10 halves. So that's 35 over 2 square units. Okay. And that's perfectly good for a final answer. Sometimes it's nice to round it to a decimal. In this case, it's exactly 17.5 square units. Okay. So that looks pretty reasonable. You know, again, I suppose if you kind of counted up the boxes here and added up the little half boxes we have, 17.5 seems about right. Okay, so you can kind of test your answer that way. Okay, now of course the other way to do these problems is with calculus, and that's what we're going to do in the next example.